Hello everyone, this lecture is about magnetic field due to currents. Actually, all the magnetic fields are generated by currents. Moving charges are necessary for magnetic fields. Even for natural magnets we talked about, there are moving little tiny bit of charges inside those materials. But we will focus on mainly if there's a current carrying wire. How does it generate a magnetic field and how we find its direction? If we put iron filings around a current carrying wire, we will see that they are also aligned in a way that as if there is a magnetic field, and there is a magnetic field there. If we put a compass, the compass will also align along the magnetic field. It will rotate and it will show us that there is a magnetic field due to a current. We find the direction of this magnetic field using a right hand rule. We'll get to that. But any type of looping current also generates a magnetic field, as you see in this figure. One loop or more than one loop, they will all generate a magnetic field. And they behave in a way to natural magnets behave. They will have a generated north pole, south pole, and they will have a magnetic field is away from north towards south, and they will behave very similar to a bar magnet. Alright, what is this right hand rule? I will call this right hand rule 1. RHR1. What we do is we wrap our fingers around the wire, keeping our thumb along the direction of the current. And once we do that, our wrapping fingers shows the direction of the magnetic field, and it is always changing. So we will draw a magnetic field line, and at any point the direction of magnetic field will be tangent to that line. Here's my magnetic field. In this part here, it goes into the board actually. I will show it with the into the board sign, cross here. That's how we symbolize into the board. Goes in and then comes back out here, out of the board, and so on. On the back there, it would be to the left if you want to draw that. At same distance away, it is the same, but direction always changes. If I go farther away, I have a weaker magnetic field, as we discussed in lecture 15. B is weaker, farther away. So for this up current, in a current carrying wire in this position, my magnetic field is into the board on the right everywhere. As I go away, it decreases, but it's always into the board, and out of the board on the left everywhere, and as I go away it decreases. Here is how we show out of the board, here's how we show into the board. Our book chooses the current to be round, cross into the board, and round, point out of the board. But I'll use the same for all. It doesn't matter. If you don't remember these signs, you can go back and check your notes always during an exam or ask me. Some more examples here. Here I have current into the board, and the direction of magnetic field would be as shown by those compasses if I put them around. Using my right hand rule, my thumb should be going into the board, and my four fingers will be showing the direction of the magnetic field. I'll try to draw that, but it's not easy. This is into the board, and this is the direction of B. Here is again how we use it. Upward current looks like that. Magnetic field is out in here, in this side. Downward current is different. Let me try that to see. As this right hand shows here, thumb is down along the current, and the magnetic field rotates in this fashion here, goes into the board on this side, out of the board on that side, as you also see in these lines over here. Curves around, comes back. Over here it would be to right, in the front it would be to left. Here are some more examples. Make sure you practice with your right hand rule to understand why these are the directions. Again, my four fingers are along the magnetic field direction. My thumb is along the current. Current here, notice, is out of the page. That's current, and current here is into the page. Make sure you convince yourself that the magnetic field lines, these blue lines with arrows, are the way they are, using your right hand rule. And then again, at any point I can draw a tangent line to those magnetic field lines. That would be the direction at that specific point, and it changes along these curves. Here's an example. A long current carrying wire extends into and out of the screen, and the compasses show the direction of the magnetic field. So I don't know the direction of current, but I know the direction of magnetic field right here. Down, right, up. So if I draw circles, it should be circles around, curving my fingers, right? Those will be my magnetic field direction. It should be in this fashion. When I apply my right hand rule, my four fingers should be curving. Let me try to draw them. So they should be curving in this fashion. And as I curve my fingers, my thumb would come out of the screen. That would be my current. So it should be out of the screen. Let's put it out here. We can imagine how those lines along a wire would go. We have a current carrying wire. The magnetic field is all along the wire. We will have magnetic field, and we can again apply the right hand rule to see that magnetic field is downward going current in this fashion. Make sure you convince yourself that magnetic field is out of the page here, into the page there, and then changes accordingly to the left there. Let me do a better job here. Tangent line, and at the back it would be to the right, so we can follow it through and see how it changes along, which is what we will do to find the direction of the magnetic field. As for the loops, our book uses this approach. We use the first right hand rule, go along the loop and draw the magnetic field lines as circles. We will be mainly interested in the center of the loop. What is the magnetic field there? And outside here we have some magnetic field. They are weaker, so stronger magnetic field is in the center, and we will only focus on that. We can use this approach to find the direction of magnetic field. Our book shows these type of figures cutting the back side of a loop and showing it in this fashion. Here current comes out of the page, and here it goes into the page. So this is out, this is in, and you imagine your current loop in this fashion. I don't really like it, but I show it because our book has it. Some questions will have it, and I'll try my best to make it clear to you what type of loop we're looking at as we solve problems. Although our book uses the first approach I've told you, I like this approach a lot, what I call right hand rule 2. And my idea here is that always we use our current fingers for the current thing. Remember, for a straight current carrying wire, the magnetic field was current, and for a looped wire, now current is current. So I can still curl my fingers along the current thing, which will be current in this case, and open my thumb, my thumb will be showing the direction of the magnetic field in the center. So this is our right hand rule too. Curling our fingers along the current and opening our thumb, that will be showing the direction of magnetic field in the center, which will be the one we are interested in. So if I have a current in the fashion on the left here, then magnetic field is down. Applying the same rule, now my current is curling in this fashion. I curl my fingers along the current, open my thumb, and my magnetic field is up in the center of that loop. Using this second right hand rule over here, this question is asking me what is the direction of magnetic field at the point in the center of the loop. Over here I have current coming out of the page here and current going into the page there. So apparently there is a loop of wire here. I'll try to draw it. Maybe I'll use dotted when the part goes into the page, dotted lines. So this part is going into the page, and I draw my current. This is coming out of the page, and over here it's going back into the page. And as I apply my right hand rule, I'm going to curl my fingers out of the page, then back in towards. As I do that, I will see my thumb would open to the right. So magnetic field at that point is to the right. I can then use this information to imagine that my current loop has a magnet in the center. Let me put that in the center actually with a different color. Has a magnet in the center, okay, and divided into two. The direction away I see here magnetic field would be its north side, and the other side would be the south side. So once I find the magnetic field in the center, I can actually go ahead and imagine all the magnetic field lines, imagining this guy here, and it will give me overall correct representation of my wire. Remember, there are lines out here. Again, we won't be calculating them, but we can imagine how they would look using this idea here. But the answer to the question, in the center magnetic field is to the right. How about for this guy? Current is out here, in there. That would look like this guy, right? Current is out here, in there. When I apply my right hand rule to curling my fingers along the current, right? Should come out here, in there. Magnetic field would be down. Magnetic field would be down. Okay, and the question is telling me what is the north magnetic pole. Whichever direction I have magnetic field, that would be the north pole. If I assume a magnet in the center, magnetic field is always away from north towards south. Again, if I wish, I can draw those magnetic field lines of the other parts as well, but then again we won't be calculating them. We will be interested in what is the magnetic field in the center, and I'm going to get to the equations in a bit. Here's a drawing given for you, and here's how it would look. So where is the north? North is in the bottom, and south is up there. Always try to imagine a magnet in the center. Once you found the magnetic field direction in the center, if you want to go into more details, if you don't need to, you found the magnetic field in the center, you're all good. Solenoid works very similar to loops because it actually many loops. That's why it's very similar. Over here, for example, oh, I made that wrong. Current goes up on this side, so it's up here, curves back around, comes back down, and we can apply the same right hand rule 2 to find it. Here this figure is showing applying right hand rule 2 to a solenoid, curling my fingers along the curling current, and my thumb is showing the direction of magnetic field. I can again go ahead and assume this is like a bar magnet. Wherever I have magnetic field away, that's my north, and then the other side will be south. To tell more details, by drawing again. If I need to, and I can go ahead and draw complete circles and magnetic field lines. However, for solenoids, magnetic field is very weak here, and again we won't be calculating it close to 0. What is the direction of the current in the solenoid as viewed from the top? If the magnetic field is given in this fashion, right hand rule, I'm gonna grab my solenoid, I'm gonna put my thumb along the magnetic field if I know only magnetic field and not the current, grab my solenoid, then my finger's rotation direction will show the direction of current, and I'm gonna answer my questions. That's what I'm gonna do here. If I look from the top, if this is my current, looking from the top, that's counterclockwise. Make sure you go over these all and convince yourself that you understand them. Don't just listen to me talking or just look at the answers. Apply your right hand rule and convince yourself that that is the direction you're looking for. Now, how do we calculate them? If I have a straight current carrying wire, this is my equation. Mu0 is a constant and it's called permeability constant. I is the current, as we always used. We use I for current again. And R is the distance from the wire. So as we go away from the wire, magnetic field decreases. As current increases, magnetic field increases. 2 pi is a constant, mu0 is a constant. So the magnetic field of a current carrying wire depends on the current through the wire and the distance away from the wire. If I take my current to be ampere, distance to be meters, this guy has Tesla meters per ampere. This T is Tesla here. And the unit for our magnetic field will be Tesla. And we'll use capital T for that. As for all the other units we have millitesla, microtesla, and we'll convert. This table here is nicely listed overall logical magnetic field strengths. And as you see, they are in the millitesla, microtesla range generally. On the surface of the Earth, it's about 0.5 microtesla. 50 microtesla, or 5 times 10 to minus 5 Tesla. A 100-turn coil is around here. How this would help you is that if you have a question and overall you want to have, if you're feeling check if your answer makes sense, you can look at here. Near a rare magnet, only we have a 1 Tesla magnetic field, or MRI solenoid has many turns of a solenoid and a strong current that could give us 1 Tesla. World largest magnet, 45 Tesla. So we overall have small values in the microtesla range, and a 1 Tesla is a strong magnetic field. It's good to have this opinion If we are finding a magnetic field of 1,000 Tesla, perhaps we are making a mistake. Alright, compared to magnetic field at point A, the magnetic field at point B is, this is my equation. Current is the same, so I'm looking at the distance. And magnetic field is inversely proportional to distance, so twice the distance, half the magnetic field. If I call the magnetic field at point A, B, at point B it will be B over 2. If everything else is the same, only distance matters. So compared to magnetic field at point A, the field at point B is half as strong. Direction, I forgot to mention direction. Apply my right hand rule. Right hand rule 1. Curling my finger, grabbing my wire, let me see it this way. I grab my wire in a fashion that my thumb will be showing the direction of current, the straight thing, remember? And then the direction of curling my fingers will show the direction of magnetic field. So here is how my fingers are curling. Oh, it goes in here, goes in and then comes back out there. That's the B, that's the magnetic field. I'll redraw that. Maybe a bit larger. My hand will be as ugly as it is, so I'll leave it. But the magnetic field, again, here is how my fingers are curling. Goes in, comes back out. So magnetic field is in this side and out on this side. Into the page, out of the page. So at point A and B, they are in opposite direction. If we have more than one magnetic fields in an area, for example, I have a magnet here, it has magnetic field lines from north to south and so on. I draw them. I also have a current carrying wire. Its magnetic field lines are in this fashion. At any point, I'm calculating magnetic field. I found field 1. I find its magnitude, show its direction. I find field 2, magnetic direction, and then I add them as vectors because magnetic field is a vector. Here in this figure, we see they are added using parallelogram method, but we know what to do, right? If we have vectors, if we can apply parallelogram easily, we can see this length, we can apply it. If we can't see anything, we set up an XY system, right? Solve all the components. The question will give us an easiness on finding the components and so on. Or if we have in perpendicular to each other, then we can apply parallelogram method and use, let's just draw here, maybe B1, B2. If they were perpendicular to each other, then parallelogram can easily be applied and use Pythagorean to find the total, right? So we already did a lot of forces as vectors, electric field as vectors. Hopefully we will be fine on finding the total magnetic field as vectors. This question here is solved for you. I'll go over it quickly. We have two wires here. Currents are equal to each other and each carry a 5 ampere current. But in opposite direction. What is the magnetic field at point P? First thing to do is to find the directions. I'm gonna roll my fingers along my wires or grab my wires in a fashion that my thumb should be showing the direction of the current. Right hand rule 1. then my fingers will be curling in this fashion if I am holding the first wire here. What does this tell me? This is my fingers curling fashion, and that's the direction of magnetic field, right? That's the direction of magnetic field. What happens? It goes into the board in here. Let's call this B1. Call this current I1, although it's the same. Name them for wire 1 and wire 2. That's the direction of B1. Everywhere on the side, it's into the board. Keep that in mind. And it's into the board at point P as well. Let me draw it just beside it. I'm going to draw B2 as well. Applying right hand rule again. Now my thumb should be in this direction, right? To curl my fingers, I curl them in this fashion now. Oh, my fingers are really weird. Let me try again. I curl my fingers. That's why they are weird. They will come out here, right? Maybe they will be. This will be better looking. Not very good, but hopefully you got the idea. My thumb should be along the current, and then I grab my wire in that fashion. This will be my fingers. And here's how my fingers are curling then, in this fashion, right? So let me not use green here, I'll use yellow maybe for B2. This is the B2 fashion. What does it do? It's out here, and it will be out everywhere on this side. As I go far away, it will decrease, but it will be out. At point P, it will be out. And it's in on this side, but I'm not interested on this side. This is my B2. So at point B, they will be opposite to each other. B1 is into the page, B2 is out of the page. So as I find their values using this equation, take 1 plus 1 minus, or just take the difference. One is in, one is out. Doesn't matter. Whoever large will be the direction of total magnetic field. So direction will be this guy because it's the larger. Direction of B total will be this guy. So either you can call them plus minus, whichever you feel comfortable with, or in or out. Whichever magnetic field is larger will win in this case. And you'll find the total value. This example will solve elsewhere and with some more examples. So I'll move away from this. This is getting a long lecture already. For the current carrying loops, if I have only one loop, this is my equation. Mu 0 again, my permeability constant, times the current divided by 2 times R. R is the radius of my loop. And this is giving me the value of magnetic field in the center. Again, we will not calculate other magnetic field values. So only the value in the center, this guy over here, for example. So out here, these weak magnetic field lines, they can be calculated, but we won't be calculating the magnetic field values. We won't be calculating them in this course. If we have more than one turns, like this guy here, if we have n turns, what we do is we multiply it by n, mu 0 and I over 2r. Again, we will find the direction using right hand rule, apply the equation to solve for the magnetic field. Over here, I have current out of the page here, then it rolls around, comes back into the page. If I apply right hand rule, that will be my case here. Again, I don't like this drawing, but that's how they draw, so I want to help you get used to it. This is what I would give you in an exam. If I apply my right hand rule too, then my current fingers along the current thing, which is current, my thumb is magnetic field direction will be up as shown in here. I find the direction, and then what I do is apply this mu0, the constant, number of turns, and current divided by the radius times 2, or diameter. This is not a nice bio question. Don't get confused when you have a real life application questions, because that's how we actually use magnetic field. So look at the values given and put them in your equation. Green turtles are thought to navigate by using the dip angle of Earth's magnetic field. To test this hypothesis, green turtle hatchlings were placed in a 72 centimeter diameter tank with 60 turn coil. When you say coil, that's this guy here. And it's not only one turn though, it has 60 turns, something like that. Imagine that right away. This is your coil. It has n number of turns, which is 60. And I am given the diameter of this to be, diameter is actually 2r, so you can replace 2r by that. 72 centimeters. 0.072 meters. Wrapped around outside. A current in the coil created a magnetic field at the center of the tank that exactly canceled the vertical component of the Earth's 50 microtesla field. What does that mean? Assuming again the current fashion is this, comes out in here, goes in here, magnetic field will be up, this case over here, and that's equal to 50 microtesla. That's what that tells me. B of this guy, let me put it here actually, 50 microtesla. Micro is 10 to 6, so 50 times 10 to minus 6 Tesla. At the location of the test, the Earth's field was directed 60 degrees below the horizontal. Oh, I should have kept reading in this case. At the location of the test, the Earth's field is directed 60 below the horizontal. I thought they gave us already the component along B. But B is, this is B Earth. Let's put it in here. This is B Earth, not B. B Earth has 60 degree tilt. We have it in this figure here too. So what I want to have is find this component of B Earth, and that is what is equal to my magnetic field, and that will be B Earth times sine 60. Embedded in an XY system over here, that's BY. We find that direction is downward, but it doesn't matter. My B coil, or B, is equal to B Earth Y. So we should be careful about the questions. Find that. You have all the other information. Put it in here. Find the current passing through the wire. Solenoid has this equation. We use right hand rule to find the direction. Use this equation to find the value of magnetic field. This dude is number of turns, this dude is length, and this dude is current. In this question we have two solenoids. One is L length, the other is 2L length. One has radius R, the other has radius 2R. Radius doesn't matter, as you can see in this equation here. One has n number of turns, the other has 2n number of turns. Magnetic fields are B1 and B2. How do they compare? If you write down this equation for both, you will see that they will have the same magnetic field, mu0 and I over L. B2 mu 0 and 2I over 2L, cancel, will be the same. If you apply the right hand rule, you will see, let's apply to this guy, the other is also the same. Current is down in here. The magnetic field will be, current is down, right? So magnetic field will be curling my fingers along the curling current, opening my thumb. Magnetic field will be to this direction, to the right. This one is a kind of a plug and chug question. A typical MRI solenoid has a length of 1 meter and a diameter of 1 meter. We don't really see the length here, but that would be something here. Diameter doesn't matter, but diameter would be something like that. Typical field inside such a solenoid is 1 Tesla, so we know B, 1 Tesla. If I assume, for example, the current is going in this direction, applying my right hand rule 2, curling my fingers along that direction, opening my thumb, that would be the magnetic field direction. I hope I could draw it nicely. So in this fashion we would have a magnetic field, and it's equal to 1 Tesla. How many turns of wire must the solenoid have to produce this field if the largest current the wire can carry is 100 amperes? So our current is 100 amperes. What is N? That's what the question is asking. This is our equation. We rearrange it, solve for N. Kind of plug and check question. But it's a neat application that we always use to map the body of a person, especially soft tissues, to understand if there's any problem or what kind of problem they might have. Here is the summary. I'm going to leave it at that. We're going to solve some more problems in another video. See you in the next lecture.